What's going on, math people? We are back, and now we're going to talk about implicit differentiation. What's that? Okay, check it. Whenever you're doing implicit differentiation, the key to implicit differentiation is knowing, if I can spell. Okay, let's try that again. Knowing which variable you are differentiating with respect to. The information below, it says with implicit differentiation, first, differentiate both sides. Next, it says differentiate with respect to x. The only way you look at this and say you're differentiating with respect to x is because in your derivative layout, x appears in the denominator. If that was the other way around and it said dx dy, then you would be differentiating with respect to y. But you know how we like to roll. We don't have all times of day and night for all this talking and just reading this math stuff. Give me some examples. So let's do it. All right, let's jump into an example. And get out of the way, we need a new screen. All right. So jumping into an example. Here we go. Sometimes you'll have to apply other rules that you've learned in the past, but the game doesn't change. Implicit differentiation. You differentiate both sides of your equal sign. And you keep rolling. All right, so your first example. We have 5xy plus y squared equals 6x plus y. All right, so you go through and you differentiate everything with respect to x. And when I say everything, I mean everything. That includes the y. All right, so if there's no x present, like in the second term y squared, once you differentiate it, you'll follow it up with dy dx. All right, so I'm going to write this out like you'll see it in a textbook or something somewhere, because we said the first rule of this is to differentiate each side. The problem said find dy dx. So we're differentiating with respect to x. So taking the derivative of each side equals d dx. This is saying take the derivative with respect to x on each side. All right, I'm going to drop that information right back in there. All right, so it can get tricky fast, so I'm going to need you to be paying attention with me. All right, so in this first piece right here, we have 5 times derivative of, check this out, we have x times y. That means we have a product rule right there. We said x times y. So we're going to apply that product rule. So we have the first, which is x, times the derivative of y, which is 1, dy dx, because we took the derivative of y with respect to x, plus the second, which is y, times derivative of the first, which was x. All right, so that is just for that first term. And it might help you if I toss some colors in here. So we have x times y. We have the y is in red. So, and the x is in black. All right, so we had the first, which is, and then we apply the product rule. Let me just slide that in there. Product rule. For this piece right here on this component. All right, so breaking it down, we have x times dy dx plus y times x. I should have started off with a simpler example, but we're already in too deep. All right, this piece came from taking the derivative of y. All right, then we have plus the second times the derivative of the first. That should have been 1. All right. And then we move on to the next term, which is that y squared. Take derivative of y squared. 2y. There is no x. So we dy dx. Now we move on to the other side of the equal sign. We take derivative of 6x. That's 6 times the derivative of x, which is 1. Plus derivative of y, which is 1 dy dx. All right, go through simplifying. We have 5x dy dx plus 5y plus 2y dy dx equals 6 plus dy dx. And everything that has a dy dx, I'm going to get it on one side of the equal sign. Everything else, I'm going to have it on the other. So we have a dy dx right here, so you're going to stay. And I have that positive 2y dy dx, so you'll stay, equals then I have a dy dx on the other side. I'm bringing it over by subtracting. And we have 6 minus 5y. Just notice all I did was move everything around. The 5y got moved to the other side. And this dy dx came to the left-hand side. All right. And we're going to factor a dy dx out of everyone. When we factor out dy dx, we have dy dx times 5x plus 2y minus 1 equals 6 minus 5y. Divide each side by 5x plus 2y to get dy, 2y minus 1 to get dy dx by itself. And we have dy dx equals 6 minus 5y all over 5x plus 2y minus 1. Alright, that is the long textbook way. What I would have said to do with this problem is I would have said move everything that has a y in it on one side and everything else that does not contain a y, put it on the other side of the equal sign. That is just me because I already know if I'm saying find with respect to x, I'm getting all the y's on one side of the equation. If it would have said with respect to y, I'm getting all the x's on the one side of the equation. Let's try a simpler example just so that you can see. Let's say we have y plus 7x equal to x squared minus y squared. Let's do that. All right. Taking into consideration what I just said, also we will want to find dy dx. Let's put the y's on one side, on the left side. So all we're doing right now is rewriting. And we have y plus y squared equals x squared minus 7x. All right. Now we're going to take derivative of both sides. Here we have derivative of y, that is 1 dy dx, plus derivative of y squared, that gives us 2y dy dx, equals derivative of x squared. We're focusing on taking with respect to x, so we're just going to differentiate like normal. All right, factor out our dy dx times 1 plus 2y equals 2x minus 7. Therefore, our dy dx equals 2x minus 7 over 1 plus 2y. Much simpler example. Hopefully that one helps you see what's happening with the implicit differentiation. All right. Yeah, whenever they toss in product rule and chain rule all inside of implicit differentiation, it can get really ugly really fast. All right, so let's slide in another example. One that is involving a trig function. But I'm just going to go ahead and warn you, it's going to get ugly really fast. But hey, I believe in you. X plus 10 of xy equals 1. All right, so I'm going to rewrite and leave all my stuff with the y on the left hand side. That's just the way I like to roll, okay? All right, so now we're going to be, this thing has embedded the product rule as the component of the chain rule there. See? So first, we have this derivative tan. We take derivative of the tan function. Tan is secant squared of the information on the inside. Right? And then multiplied by the derivative of the information on the inside. Notice we got a product rule going on there. What we're trying to find is find dy dx. we have a product rule going inside our function. So we're going to take the first, which is x, times the derivative of the second, which is y, plus the second, which is y, times the derivative of the first, which is x. That took care of the left-hand side of that equal sign. Go to the right-hand side of that equal sign, take the derivative of 1, that is 0, minus the derivative of x, that is negative 1. So we have secant squared xy times x dy dx plus y equals negative 1. Alright, so we got some stuff we need to be doing. Alright, so we're going to go ahead and distribute this thing right quick. We have x, that's x dy dx, secant squared xy, because we're distributing secant squared xy throughout this green parenthesis. Secant squared has to be distributed through that, plus y secant squared xy equals negative 1. Alright, we're trying to get dy dx by itself, so we're going to have x dy dx secant squared xy equals negative 1 minus y secant squared xy. Everything is henceforth is algebra. Alright, we move this piece on over, this whole section here, by subtracting it. Dividing each side by x secant squared xy, we get that dy dx is equal to negative 1 minus y secant squared xy over x secant squared xy. Implicit differentiation will take a little practice, but it's just something that you get used to by doing more and more examples.